Work causes a change in energy. This is known as the work-energy theorem, and we're going to spend probably the rest of the class today talking about it. It's really, really important that you understand work-energy theorem. You can use this idea to solve all your old kinematics problems now. All those problems with objects rolling down hills and things like that that are kind of ugly to solve in kinematics, you can use energy for those. It's just an alternate form. How fast does a ball go when you drop it? Energy. If you throw a ball up, how high does it get? Energy. How fast is it when it gets to the ground? Energy. You can use energy to solve almost every kinematics type except for projectiles. Projectiles, you're stuck. You got to use kinematics equations for that. But now you're going to have two ways to solve those kinematics equations. And either one is acceptable. Whatever you think of first, do it that way. If you come up with energy first, go for it. If you come up with kinematics first, go for it. A lot of people will come up with kinematics just because we've been doing it over and over again. They don't like to change. Sometimes this is easier, sometimes not. Again, it's whatever you think of first. If you do positive work, you increase the energy. If you do negative work, you decrease the energy. Work causes changes in energy. The two forms of mechanical energy that we're going to talk about are potential and kinetic. Within potential, there are several different types as well, but the broad scheme of that is potential. Jane uses a vine wrapped around a pulley to lift a 70-kilogram Tarzan from a treehouse 9 meters above the ground. How much work does Jane do when she lifts Tarzan? Excellent question. I'm so glad you asked. Thank you. Draw a picture if you don't have a picture already. We got basically a pulley system. It's wrapped around a pulley. Here's your treehouse. Up in the trees. We got a pulley system. Here's Tarzan. I won't use T. That's about the worst variable I can use. Tarzan, and here's Jane. No, it's wrapped around his waist, right? That didn't improve the situation. The waist is down here. So, whatever. So Jane's down here, and she's doing this pull thing. All right. So here's Tarzan, and he weighs 70 kilograms, and he's going up to the treehouse, and that treehouse is 9 meters up. It really doesn't matter how attractive your drawings are. You could do dots for people. I started with squares. That was probably a better idea. So how much work does Jane do? Well, if I want to know how much work Jane is doing, I need to know how much force Jane is applying. How is Jane lifting up Tarzan? What force is she using to do that? She's using tension. Dealing with a force problem, good idea to have a free body diagram. We're talking about the work done on Tarzan. So free body diagram of Tarzan looks like this. Which of those forces is doing the work? Tension is doing the work. So from our free body diagram, instead of going F equals ma to solve for forces, we're going to go work equals force delta x cosine theta to solve for work. The force is tension. What's the tension? In this case, it's mg. You can show that. Sum of the forces is 0. We'll assume that he's going at constant velocity. So tension minus mg equals 0. Tension equals mg. If he's accelerating upwards, then she has to do additional work to accelerate, because she has to apply additional force. We'll do a problem like that later on, but just so you know, If it's accelerating, you work at the same problem the same way. So we do a substitution, mg in for tension. Work equals mg delta x cos theta. Mass, 70. I'm going to omit the units just for space. Distance that she's lifting him, 9 meters. Cosine of the angle between the force that she uses and the displacement. What force is she using? She's using the tension. Even though we did a substitution for mg, it's the tension that's applying the force upwards. Displacement is up. Tension is up, so the angle between them is 0. 70 times 10 times 9. Cosine of 0 is 1, and the unit of work, the joule, or newtons meters. So Jane does 6,300 joules of work on Tarzan. And that's how you solve work problems. It's always the same method here, too. Force, delta x cosine theta. Sometimes there's an intermediate step here to solve for the f value. Sometimes it's obvious, sometimes there's an intermediate step. Then you plug it right back in and solve, work the rest of the problem. For part B, how much work does gravity do? Negative 6,300. The force is the force of gravity, which is downwards. The distance is up, so the cosine of theta is negative 180 degrees. So gravity does, work done by gravity equals negative 6,300 joules.